Welcome everybody to our next video on applied problems. And so what do we really mean by an applied problem? Basically we're taking a real world problem, and from that real world problem we translate it into the language of mathematics. Now what that gives us is either some kind of an equation, or it's going to give us some kind of picture from geometry. From there, once we're in the world of mathematics, now we can use the properties of mathematics to go about finding a mathematical solution to the problem. Then once we have the mathematical solution, the idea is to translate that mathematical solution back into the real world so that we obtain a real world solution to our real world problem. Now the question is really, how do we go about doing this? And it's all about translation, probably from the real world problem into the world of mathematics. Now this is this brings up the true applicability of mathematics to the real world. Now that's probably summed up best by a quote from physicist Eugene Wigner, who was a physicist who worked on the Manhattan Project, developing the first nuclear bomb. Now, he was saying this strictly from a secular worldview, and what the quote actually is that the miracle in the way the language of mathematics fits the laws of physics is a wonderful gift which we neither understand nor deserve. Now that's a pretty profound statement coming from an incredible admission coming from that secular worldview, whereas we who are Christians and hold steadfastly to this Christian worldview, we take a very different stance on it. And what this kind of big question is, why does mathematics seem to fit the laws of the universe so well? It's because, well, it was designed to be that way. And this is really kind of evident from Psalms 19, verses 1 through 4, where the psalmist writes, "The heavens declare the glory of God, and the sky above proclaims his handiwork. Day to day pours out speech, and night to night reveals knowledge. There is no speech, nor are there words. Their voice is not heard. Yet their voices go out throughout all the earth, and their words to the end of the world." God's creation does reflect this wonderful beauty that he also put into mathematics. Both of them are wonderful gifts. Wigner's quote is correct, and neither one of them do we deserve. Neither do we deserve salvation, but yet God freely provides that for us. And so kind of this big question of why is math so applicable to the real world, it's because God designed it that way. So now let's take a look at actually some of the problems that we have in this setting. So the first problem that we have is something like, say, 12 plus 9 times a number is 156, and our job is to find the number. Well, the solution in that setting is really just to almost translate verbatim the sentence into the language of mathematics. Now our sentence says 12 plus 9 times a number is 156. Well, 12 translates pretty well to the number 12. Plus, again, translating the operation directly to addition. 9 times a number, well, 9 is obviously the number 9, times is the operation of multiplication, and then a number, the unknown, we can just write that as an unknown variable, n. Now the word is, in most mathematical statements, or most kind of applied problems, is going to translate to equals. And so we've got is equal to 156. Now what that gives us is our equation 12 plus 9n is equal to 156. So we've translated it from the real world question into the language of mathematics, and now we have to solve that equation. So starting with 12 plus 9n is equal to 156, we can subtract 12 on both sides. which is just going to give us 9n is equal to 144. We divide both sides by 9, in which case n is equal to 144 divided by 9, or 16. Therefore, the number n in our unknown question is 16. Kind of looking at another problem now. Suppose that a man has $56.95 with which to buy gas. If gas costs $3.35 a gallon, how many gallons may the man buy? Well, kind of one natural way of looking at this problem is that to visualize this equation with units involved. And so we've got cost is going to be equal to our cost per gallon times the number of gallons. Now, kind of the beauty in this, we see gallons in the numerator. We also see gallons in the denominator. And so, mathematically speaking, those gallons units should cancel out, numerator and denominator, just leaving us with a variable of, or units of, cost. So this is, again, kind of a pretty intuitive notion. Let's see how that translates to the math. Well, if we let C be the cost of the gas that we have, G being the number of gallons of gas which we buy, then our kind of pseudo equation that we had, that cost is equal to cost per gallon times number of gallons, just becomes C is equal to 3.35, because $3.35 per gallon was the price of gas. So $3.35 times G. And so our total amount of money which we have is $56.95. We've got an equation, 56.95 is equal to 3.35 times G. Well, if we divide both sides by 3.35, we obtain that G is going to be 56.95 divided by 3.35, or 17 gallons. Therefore, the man can buy a total of 17 gallons of gas. Kind of looking at a third problem that we typically occurs when you're talking about applied problems is percent increase or percent decrease. Now, in this situation, we have a mechanic who must raise his hourly rate by 2% to cover increased costs. We know that his new rate is going to be $27.14 per hour. What was his previous rate? Well, one thing that we need to remember is that when we're talking about percent of a number, that actually means the percentage as a decimal number times the number itself. And so what we see here again is the translation of the word of being translated to the operation of multiplication. So of really gives us multiplication in that case. And so for a percent increase, we can kind of do another one of these pseudo equations where we've got our new amount is going to be equal to our old amount plus whatever the increase was. Now, we've got R being the old rate that the mechanic was charging, then what we have is that $27.14, his new rate, is going to be equal to his old rate plus the increase. Now, the increase was 2% of the old amount. And so, again, that 2% of is going to be 0.02 times the old amount, R. So this gives us an equation, 27.14 is equal to R plus 0.02R. Well, we can combine like terms. There's a coefficient of 1 in front of this R, so 1 plus 0.02 is 1.02 times R. And this is the equation that we need to solve. So taking 27.14 equal to 1.02R, we can divide both sides by 1.02, which gives us 26.60784,314 equal to R. Now again, kind of translating this back into a real world problem, we're going to round it to the nearest cent, and so what we find is that the old rate is going to be approximately $26.61 per hour. So this has been kind of 3 examples of kind of working with word problems, how particular words like is will translate to equals. The word of is going to translate to the operation of multiplication. So how those translate into the language of mathematics, which then gives us an equation that we can turn around and solve. So I hope this has been a little bit insightful and will help you along with solving your own applied problems. And I will see you guys next time.